Well, hello again, everyone. Welcome to our discussion of section 3.7, where we will talk about rational functions and their graphs. Rational functions are basically functions of two linear functions or quadratic functions divided by each other. And before we get too deep into that subject, I want to remind everyone to please read or skim through the textbook section in section 3.7, and then watch this video after you've read the textbook or attend the class, and then review your lecture notes with all the problems that you saw either solved in class or in your book. Solve all those problems on your own again without looking at the solutions you have. And then, of course, complete all the assignments by the due date, and then review throughout the semester. Okay, so the basic structure of a rational function is of this type. So you have, in this case, the rational function is called r of x. You can call a function anything, so that's what it's called, equals a function which we call p of x divided by another function q of x. Okay, so how do we sketch? The main topic here in this section is graphing these rational functions, which involves a lot of things. It involves finding any potential, any asymptotes, vertical, horizontal, or slant asymptotes. It involves finding the x and y intercepts, and finally graphing these rational expressions or functions. So just the graphing of these rational functions, it involves quite a bit. So sketching the graph of the function, these are the fundamental steps. First, we want to factor the numerator, then factor the denominator. We've done quite a bit of factoring so far, right? So we're going to continue doing that for both numerator and the denominator of a rational function. Then find the x and y intercepts, and also find any vertical. These are very important because there are a number of different asymptotes we can have. So either any vertical asymptote, or a horizontal asymptote, or a slant asymptote. One thing I want to highlight at this point is that it is possible for us to have both vertical and horizontal asymptote at the same time. We can have these at the same time, but we cannot have a horizontal and slant asymptote at the same time. We either can have a horizontal asymptote or a slant asymptote. If we cannot have a horizontal asymptote, then we must have a slant asymptote, and vice versa. Okay? And there's a very quick and easy test we can run in order to know if we're going to have a horizontal asymptote or not. We'll get to it in a few minutes. The other thing I wanted to highlight is, and I mentioned that in the parentheses here, either a horizontal or a slant asymptote is possible, but not both. Okay? So, and you should read the rest of this small paragraph, because all of this is a summary of what you find in your book. If you've read the book by now, then you'll know what I mean. This is a summary of all of that. So an asymptote is a boundary line. I'm defining what an asymptote is here. An asymptote is a boundary line such that the graph of a function can get very close to it without crossing it. So right after this, I add a very important statement afterwards. It says, a vertical asymptote cannot be crossed by the graph line, but a horizontal asymptote may be crossed. And we will next look at examples of asymptotes. Okay, so that basically covers everything I wanted to say. Very, very important to remember these 4 steps as you draw graphs of rational functions. So factor the numerator, factor the denominator, find the x-y intercepts, and then find the asymptotes. Vertical, horizontal, and or horizontal or a slant asymptote. Okay, so here are a few examples of the graphs of rational functions. For example, this one has a slant asymptote. What you see as a dashed line here is an asymptote, but it's slant. It's not vertical or horizontal, it's slant asymptote. You can see the graph of this rational function comes very, very close to it on this side, but it will never touch it. So the vertical and slant asymptotes cannot be crossed, but horizontal asymptotes can be crossed. Okay, so the other example of the graph of a rational function would be this one. So notice in this case, we have a horizontal asymptote. So for sure, we're not going to see a slant asymptote, right? We can either have a horizontal asymptote or a slant asymptote. If you have a slant asymptote, then you know for sure you're not going to have a horizontal asymptote. But take a look at this side, which I should have mentioned when we talked about this graph. Along the y-axis, it seems that there is another asymptote. It's a vertical one. So along just looking at the behavior of this curve, as it approaches the y-axis, it's obvious that we have a slant asymptote, right? That's obvious. But also on the side where the line of the curve approaches the y-axis, there seems to be a vertical asymptote, which would be the y-axis. Okay? So here we have a horizontal asymptote. That means for sure we're not going to see a slant asymptote. Okay, but we do have a vertical asymptote. So the horizontal asymptote is the only kind of asymptote that may be crossed by the curve or the graph of the rational function. Okay, but vertical asymptote and slant asymptotes cannot be crossed by the graph. Okay, so next we'll have to sketch some graphs. Let's see what we have in store on the next worksheet. Oh, that was the 5th step. So this one, number 5, sketch the graph. So after you've done all of this, factoring the numerator, the denominator, finding the xy intercepts and the asymptotes, then this 5th step is sketching the graph. But we will get to our examples soon enough. So finding the vertical asymptote, that's the easiest one to find. So given a rational function like this, any value that would make qx is the denominator. So let me make this clear. Qx is the denominator. Any value that would make the denominator equal to 0 would be a vertical asymptote. So at that x value, the rational function cannot attain a value, cannot have a value at that x value that would make the denominator 0, right? We know that we cannot have the denominator of a fraction be a 0, because in that case, the fraction will be undefined. So that's how we find the vertical asymptote. The horizontal asymptote there are 3 cases for finding the horizontal asymptote, where it is going to be. Okay? So if, this is case 1, if the degree or the highest power of p of x, that's the polynomial in the numerator, if the degree or the highest power of p of x is less than than the degree of qx, that's the polynomial in the denominator, then the horizontal line is always y equals 0, which would be the x-axis. Y equals 0 is the equation of the x-axis. So then y equals 0 or x-axis is the horizontal asymptote. So what would be an example of this kind of situation? So if we write an example of that, then I'm going to use r of x just to be consistent with this. So if r of x is equal to x minus 4 and divided by x squared, right? Even a rational function like this will give us a horizontal asymptote, which is the x-axis, or at y equals 0. Because the degree or the highest power of p of x, the degree of this is 1, is less than the degree of q of x. The degree of the q of x, which is the polynomial in the denominator, is 2. So 1 is less than 2. So we're going to have a horizontal asymptote at y equals 0, or the x-axis. Okay, that's an example of this case. Let's show a graph of this. So I'm going to go to the computer and graph this for us to see exactly how that works. So here we have this, okay, so r of x equals, what did we say? We said x minus 4 divided by x squared, right? Like that. So this, what you see on the screen, is the graph of the this rational expression. So notice that the x-axis is the horizontal asymptote, right? You can see it clearly. That's the x-axis. Look at the behavior of these graphs. And if I zoom out, you'll see it. I'm going to zoom out and then zoom in again. Notice that? How the line of the graph is approaching the x-axis in here. So let me zoom in so you can see that in this case, in fact, the graph did pass or cross the x-axis right there. Do you see it? Right there. This is what we were saying earlier, that the horizontal asymptote is the only asymptote that can be crossed. Not that it will be crossed, but it can be crossed. Right there, the graph of this rational function is crossing the asymptote, which is the x-axis. And where is that crossing? Take a look at the equation. That's the x-intercept, right? The x-intercept is wherever this expression is, the y value, or r of x, is equal to 0. Where r of x could be 0? Well, anytime you have a 0 in the numerator of a fraction, the whole thing will be 0. 0 divided by anything is 0. So when x minus 4 equals 0, then you're going to have this rational function be equal to 0. That's where this x-intercept is happening. Okay? So where is the numerator equal to 0? Well, just set it equal to 0, x minus 4 equals 0, and solve that for x. You get x equals 4. So that point that you see where the graph is crossing the x-axis right there is the point 4, 0, right there. Okay? We can label it. We can quickly snap to it and label it. Okay? So this is that. All right, let's switch back to the dock camera. And again, I apologize for that screen glitch that you see when I switch back and forth between the dock camera and the computer. You're going to see that screen glitch. So I apologize for that. I might be able to go into the video later on and edit it out, but it's less than a second long, so I might not be able to do it, but I'll see if I can delete that glitch. Okay, so the second case, if the degree or the highest power of p of x, which is the polynomial in the numerator, is equal to the degree of qx. So if the powers are equal, and here's an example of that. So for that, let's give this example. R of x equals, I'm going to change this so it's going to be x minus 4 divided by x plus 3. Right? So look what I did. I changed this rational function so that now the degree of the numerator and the degree of the denominator are equal to each other. They're both 1, right? In the first case, the degree of the numerator was less than the degree of the denominator. That's when we had y equals 0, or the x-axis be the horizontal asymptote. But what happens now that the degrees are equal? Well, the asymptote can be calculated using this formula. If the degrees are equal, this is the formula to calculate where the horizontal asymptote is. So this is basically what all of this formula is equal to y. So in this case, the powers or the degrees are equal. We use this. The leading coefficient of p of x, the leading coefficient is the coefficient of the leading term. Remember from last time, the video from last section? The leading term of any polynomial is the term with the highest power. The coefficient of that leading term is called the coefficient of the leading term. So in this rational function, the leading term in the numerator and the denominator is just x. What is the coefficient of the... we can change this just to make it more interesting. So let me change the coefficient of the x in the denominator to 2x plus 3. Okay? That'll make it even more interesting. So look at the coefficient, because the powers or degrees are equal, then the leading coefficient of p of x, okay, the leading coefficient of p of x is 1, divided by the leading coefficient of q of x, that's 2. 1 over 2 is the horizontal asymptote. So y, in this case, y equals 1/2 is the horizontal asymptote. Okay, where is the 1/2 coming from? Once again, the 1 is the coefficient of the leading term in the numerator divided by the coefficient of the leading term in the denominator. This makes, I just chose this example, but let me give you another example on this piece of scratch paper. Suppose if you had the rational function x 3x cubed minus 1 divided by 2x cubed plus 5, right? Suppose you had that as your rational function. So once again, the leading terms are 3x cubed and 2x cubed. Look at the degree of the polynomial in the numerator, it's 3. The degree of the polynomial in the denominator is 3. So it's again case 2, where the horizontal asymptote would be the ratio of the coefficient of the leading term in the numerator and divided by the coefficient of the leading term in the denominator. So it still would be the same formula. So here, y equals 3/2 would be the horizontal asymptote. Okay? This goes for anything. So just suppose, let me give you another example. Suppose we had minus 2x to the fifth plus 3 divided by 7x to the 5 minus 1, right? Suppose we have this ratio in a rational function. Well, look at the leading terms again. Now, they have the same power, right? Because of that, the horizontal asymptote would be the ratio of their coefficients. So y equals minus 2 over 7 would be the equation of the horizontal asymptote. Okay, I hope this is clear. Okay, so then the third case is that if the degree or the highest power of p of x is larger, let's graph this. We graphed that one. Let's graph this on the computer before we move to case 3. Okay, let's do that. So once again, we're back here. Let's delete this. And our example was x minus 4 divided by 2x plus 3. Okay, so if I zoom out, notice that that's the graph of the rational function that you see on the left here, on top of the screen on the left. This is the graph of that. You can see there is a horizontal asymptote, right? There's definitely a horizontal asymptote. There's definitely a line, a horizontal line, where the graph, these two pieces approach it and get very close to it. And so what is that line? We determined that was 1/2, right? The coefficients of the leading terms divided by each other. So let me graph y equals 1 over 2 right there. You can see now, you can see the line, which is the asymptote of these, the graph of this rational function. We can zoom into it. We can zoom to it like that. See? On both sides, the graph is approaching the green line very, very closely, but it looks like in this case it will never touch it. Of course, over here in this, on this end, it looks like they're touching, but they're really not touching. I mean, we can zoom in, but it'll be a waste of time. See, we can zoom into it. You can see that they become almost parallel, but they will never touch on that end. So we can zoom out, or zoom out like that, and zoom in on this side, on the right side. Take a look. Well, it looks like, do they cross on this side? Let's see. Let me zoom in. I don't think so. Yep, they do not cross. See, the line, the green and the red line are becoming parallel almost, but they will never touch. So if I zoom out again, or zoom in, so you can see how that graph behaves, right? So we have the horizontal asymptote at y equals 1/2, and the red curves are the graph of the rational function. Okay, let's get back to the dock camera and look at the third case. So if the degree or the highest power of the polynomial p of x is larger than the degree of q of x, so if this p of x has a power, the leading term here, if it has a higher power than the leading term in the denominator, then there is no horizontal asymptote, right? There is no horizontal asymptote. So what do we have instead? Instead, we have a slant asymptote. So when does that occur? It occurs when the degree or the power of the polynomial in the numerator is larger than the degree or the power of the polynomial in the denominator. This is an example of that. So I'm going to put that example here. Suppose we say 2x squared plus 1 over x minus 3. Right? That's a rational function. Compare the leading terms, which are 2x squared in the numerator and x in the denominator. The power in the numerator is higher than the power in the denominator. When it was less than that, when the power in the numerator was less than the power in the denominator, then we had the horizontal line, or y equals 0, or the horizontal axis, x-axis, was the horizontal asymptote. But this is the opposite. The power in the numerator is larger than the power in the denominator. So that means we do not have a horizontal asymptote. Instead, we have a slant asymptote. And we will look at how, next we will look at how to find the slant asymptote. Okay? But meanwhile, let's go back to the computer and graph this rational function to see how the slant asymptote is there. Okay, so we are going to enter. I had 2x squared plus 1 divided by x minus 3. Okay, you can see let me zoom out. You can see the two pieces, right? Clearly you can see that there is a slant asymptote right there going in between those two pieces in a slanted fashion between those. So you might be wondering, well, how do we know where that slant asymptote is? Well, that slant asymptote has an equation because it's going to be a linear or straight line, right? It's going to be a straight line going in between these two pieces. And we can say, well, we can ask, well, how do we know what that line is or where that line is? Well, take a look at this rational function that you have on the screen, on the left side here in this corner. If you use a long division or a synthetic division, you're going to be able to find where that slant asymptote is. Are you curious about that? I'm guessing some of you might be curious about how do we find that slant asymptote. So even though I didn't have a plan, I just made this example up. I just made it up. Even though I had no plans to find the slant asymptote of it at this point, but I'm guessing those of you who are watching this video are curious to know where that slant asymptote is, or what that equation of that slant asymptote is. So let me show you how we find that. Okay. And then we'll do more examples in the worksheet as well. So I'm going to switch to the dock camera. So here is and we'll go back to the computer to plot the slant asymptote. Okay, so let me first write down the function we have, which is 2x squared plus 1 over x minus 3. Okay, so this is our function, right? 2x squared plus 1 over x minus 3. So we know that we're not going to have a horizontal asymptote because the degree of the leading term is higher than the degree of the leading term in the denominator. Okay? So now that we know we don't have a horizontal asymptote, how do we find the slant asymptote? How do we find the slant asymptote? Well, use the long division In this case, we could also use a synthetic division. Okay, it makes no difference. So I'm going to use the long division. So we have 2x squared plus 1 divided by x minus 3. So what do we have to have? Let me cover that piece. What do we have to have up here to multiply by x to get 2x squared? Well, we know that we need a 2, so 2 times x is 2x, but we have x squared, not x, so let's put another x there too. Okay, so then let's distribute this to all of this. We get 2x squared minus 6x. Then, as soon as you run out of terms to multiply by, 2x times minus 3 is the last term. So put a parenthesis around it, put a minus in front. Now let's subtract. 2x squared minus 2x squared, that adds up to 0. Is there an x term up here? No. Do we have an x term down here? Yes. So just minus 6x will be positive 6x, right? Is there a constant here? No. So there's nothing to subtract from 1. So we're going to write down the 1 right here. So now we ask ourselves, what can we put up here? What can we put up here to multiply by this x to get 6x? Well, we already have x, so plus 6. Okay, so now let's distribute 6 into this. We have 6x, 6 times minus 3, right? That will be minus 18. 6 times minus 3 minus 18. Then like that. And then we have the 6x minus 6x, 0, 1 minus minus 18, minus 19. Okay? So what do we have here? We have this is the remainder, right? That is the remainder. And so if we rewrite the original polynomial, so the original was 2. So here's what we have. We have the 2x plus 6, that's the quotient. The r of x is equal to 2x plus 6, which is the quotient, minus 19 divided by x minus 3, right, which was the divisor. That's our remainder, minus 19 divided by that. Now, this linear piece, y equals 2x plus 6, okay, is a slant asymptote for this rational function. So did you see how we arrived at that? We know this power being higher than this power, we know we're not going to have a horizontal asymptote, so instead we have to have a slant asymptote. How do we find the slant asymptote? We use long division to divide this by this, and we did that here. And what did we end up with? With this quotient, right? This is the quotient we ended up with, quotient. From up here, ends up here, minus 19, which is the remainder divided by x minus 3. Now this quotient, which we arrived at here, that quotient is the slant asymptote. So just set it equal to y. Slant asymptote. That's the equation of it. 2x plus 6. So let's go back to our computer and plot that line with the graph we already have. Okay, here it is. So we have y equals 2x plus 6. Do you see that? As soon as I entered the equation of that straight line, you can see that purple straight line snapped right where the slant asymptote should be. We can zoom into it if you like that. Do you see that? The purple line, that straight line is the slant asymptote. And look at the behavior of the line of the graph of the rational function with respect to that purple line. Look at it. They get very close to each other, but they do not touch, right? We can zoom in as much as we want, right there. See? When we zoom in, they become parallel, but they do not touch. The purple is the straight line 2x plus 6, and the red line is the graph of the rational function. I hope this is all making sense as you watch the video. Okay, right there. So maybe I should zoom in a little more like that. Okay, that's the slant asymptote. Okay, so let's get back to the dock camera. So as we were talking about that, we were really heading in the right direction, finding the slant asymptote. So we just did it. I thought, since I just made that example up, I thought, why not show it graphically? But that was coming up, right? So we were on the right course. So finding the slant asymptote, given a rational function, use either the long division or the synthetic division when possible, right? We know that synthetic division has limitations because when the x term in the divisor has a coefficient other than positive 1, like 2x, 3x, and so on, we cannot use the synthetic division. We must use the long division. But if x has a positive 1 coefficient like that in the divisor, then we can use the synthetic division too, as well as the long division. Okay, so then to obtain, use either long division or synthetic division to obtain this that we just did, right? In our case, the quotient was 2x plus 6, right? If I remember correctly. It was 2x plus 6, so we plotted it and we saw how the slant asymptotes look, where the r of x is the remainder and the term ax plus b set to y equals x plus b is the slant asymptote. So you just saw an example of that. Okay, so that was basically the gist of how to find the graphs of rational functions. Now we're going to go over some examples. So here, for this example, number 1, they don't want us to graph these. We will do that in a few minutes. But for these two examples, all we have to do is find the x and y intercepts. That's all. Okay, so let's do that. So the x-intercept is wherever y equals 0, right? Wherever r of x equals 0. So let's set it equal to 0, and then x minus 5 divided by x plus 6. When is this rational function equal 0? Whenever x minus 5 equals 0. So therefore, x minus 5. If the numerator is 0, this whole thing becomes 0. So therefore, x minus 5 must be equal to 0. So x equals 5. Therefore, the x-intercept is 5, 0. Okay. What about the y-intercept? The y-intercept happens when x is equal to 0. Right? So, in that function, let's substitute for x with 0. So we have y, I'm just substituting r of x with y, equals 0 minus 5 divided by 0 plus 6, right? So what is that equal to? That is equal to y equals minus 5 over 6, which means the y-intercept is 0 comma minus 5 over 6. Okay? All right. So, like I was saying earlier, they're not asking us to graph this, but why not graph them and see how these two plot? I mean, not this one, but this one, not this one, just part A. Let's graph this. So we're going to go back to the computer. And we have the r of x equals x minus 5 divided by x plus 6. Okay? So there we have the plot. We have the plot of our of the function. So we found that the x-intercept was at 5 comma 0, right? Let's snap to it. 5 comma 0, right there. And let's zoom in on it, right there. You can see that red dot. Let's label it 5 comma 0. Right there we have an x-intercept where the graph crosses the x-axis. So what about the y-intercept? We found that the y-intercept was 0 comma minus 5 over 6, right there. And let's label it like that. So it gives us the decimal form of minus 5 over 6, which is fine. But that's where it is, the y-intercept and the x-intercept. Okay? Like that. One other thing that I hope you're catching from all of this graphing is that the rational functions always come into two pieces, at least two pieces, right? At least two pieces. So that's a dominant feature or a very recognizable feature of graphs of rational functions. Every time you see a graph like this split into 2-3 pieces, then you have a rational function. Okay, so let's go back to our dot camera. So the second example here, or part B, once again, let's find the x-intercept. That's when y equals 0, y or r of x equals 0. So we have 0 equals x squared minus 25 over x squared, right? When is this whole fraction equal to 0? Any fraction is equal to 0 when the numerator is equal to 0. So this is such an easy expression in the numerator that I didn't bother to factor it. If you wanted, we could. But it's such an easy one, so we can do without factoring it. We can see where that numerator is 0, equal to 0. So x squared minus 25 equals to 0. So from this, we're solving for the numerator being 0. We want to know when that happens. So then x squared equals 25. And then by square root property, we have x equals not just 5, plus or minus 5. Remember? By square root property. So the x-intercepts are 5 comma 0 and negative 5 comma 0, right? These are the x-intercepts. So let's find the y-intercept. That's when x equals 0. In this function, let's substitute for x with 0 and find y value. So y equals 0 squared minus 25. Oh, we will not have, I just noticed, so divided by 0, so this is undefined, which means no y-intercept exists, right? Because at that point, the graph is going to be undefined, or the function is going to be undefined. So undefined, which means no y-intercept exists. Okay, so we're going to go back to the computer and plot this rational function, and at least look at the x-intercepts. Okay, so in this case, I mean, you'll see it now in a minute, but x equals 0 is going to be the vertical asymptote. Okay, in this case, they're not asking us to find the asymptotes, but looking at this, because we can't have x equals 0, so we're going to have a vertical asymptote at x equals 0, which would be the y-axis. So the y-axis would be a vertical asymptote, but let's plot it. Okay, so we have here, I'm going to first plot the rational function, which was x squared minus 25 divided by x squared, like that. Okay, so right there you can see that definitely the y-axis is a vertical asymptote, right? Do you see it? You can see this trough type of a shape dropping down like that around the y-axis. Look at that. So clearly the y-axis is a vertical asymptote. So let's go back up again. So the asymptotes, right? We would expect those to be at minus 5, comma 0, and 5, comma 0. You can already see them, right? Like that. So let's snap to them, those points. So 5, comma 0, right there, and we're going to label it. And then also let's snap to negative 5, comma 0, and label it like that. Okay? So those are the x-intercepts, and clearly the y-intercept is an asymptote. Okay, so let's go back to the dock camera. Okay, now here, in this example number 2, they're asking us to do the whole thing. They're asking us to find the x and y intercepts, the asymptotes, and graph the whole thing. Okay, wonderful. We're going to do all that. So we're going to do this in the order they ask us. First of all, remember that first page that the procedure to graph was factor the numerator, factor the denominator, and then find the x and y intercepts? In this case, we don't need to factor, right? I mean, you can factor that 2 times x plus 3, but it's still, what that means is if you have factors that are binomials, you can factor the 2 out, but it's not going to make this a whole lot of difference. Where factoring would be very, very critical is if you can break this up, either this or the expression in the denominator, into 2 binomials. So x plus 3 times x minus 3, something like that. Or x plus 6 times x plus 2, or x minus 2. If you can factor the expression like that, that would be critical to do, because with that you could find the intercepts easier. That's all. Okay, so now we want to find the x-intercept, which is where the y value is equal to 0. So I'm going to substitute 0 for that, and then that is equal to 2x plus 6 over minus 6 plus 3. So when is a rational function equal to 0? When its numerator equal to 0. So therefore, 2x plus 6 equals to 0. If this is the case, then this must be the case, which is the numerator equal to 0. Let's solve for x using this. Minus 3, right? So the x-intercept is at negative 3 comma 0. Okay, we got that. Let's find the y-intercept. I'm going to do that here so we can look at all this on the screen at the same time. So y-intercept, it happens where x equals 0. So let's replace x with 0 in here. So y equals 2 times 0 plus 6 divided by minus 6 times 0 plus 3. And so that'll be 0 and that'll be 0. So 6 over 3, it'll be 2. So the y-intercept, it would be at 0 comma 2. Right? That's the y value, 0 comma 2. Then they're asking us to find the asymptotes. Well, let's find the vertical asymptote first. That's always the easiest. So vertical asymptote. That's when the denominator equals to 0. So we should set minus 6x plus 3 equal to 0 and solve for x to find where the vertical asymptote is. So minus 6x plus 3 equals 0. Minus 6x equals minus 3. X equals minus 3 divided by minus 6, positive 1/2. Right? That's the vertical asymptote. So the question is here, do we have a horizontal asymptote? Because if we do, fine. If we don't, then we're going to have to find the slant asymptote. So it's critical to establish we have a horizontal asymptote or not. Well, take a look at the leading terms in numerator and the denominator, right? The leading term in the numerator is 2x. The leading term in the denominator is minus 6x. So their powers, the degrees, are equal. So we do have a horizontal asymptote, and that was the case 2. I believe that was case 2, right? Let me bring it back up again. So this is on page 2 of this worksheet. If the degree or the highest power of p of x is equal to the degree of q of x, that's that. If they're equal, the degrees are equal, then the horizontal asymptote can be calculated using this formula, which is the coefficient of the leading term in the numerator divided by the leading coefficient of q of x. Okay? So in that case, so let me write this down. Horizontal asymptote, because the degree of two of it, the numerator and the degree of the denominator are equal. So because the degrees of the numerator and the denominator are equal, then the horizontal asymptote is simply the ratio of the leading coefficients. So 2 over minus 6. So y equals, or let me write this with a different color, y equals 2 over minus 6, or after simplifying, y equals minus 1 over 3, right? That's the horizontal asymptote. Okay? So next for us is to graph this, and I need to grab my ruler here. And after this, we will go to the computer just to see, because I'm sure my manual drawing is not going to match what the computer can do, and I will move this up. And so we'll have this, the manual drawing, as well as the computer drawing. So this would be r of x, which is what the, or y-axis, either or. And we'll have the horizontal axis here. Oops. Like that. All right. So let's plot the asymptotes first, because we're going to know where those limitations are. So the vertical asymptote is at x equals 1/2. So I'm going to increment. These are nice, easy numbers, all of these, -3, 0, 0, 2. These are small, easy numbers. So I'm going to make my increments a little bit large. So 1, 2, 3, and then 1, 2, 3. So there'll be 1, 2, 3, -1, -2, -3, and then let's see. So we have -1, -2, and then 1 and +2, right? Okay, so the vertical asymptote is at x equals 1/2. So x equals 1/2 would be right here, halfway between that, 0 and 1, right there. So I'm going to drop a dashed line right through it. Dashed because it's not the graph, it's just the asymptote. So we know that the vertical and slant asymptotes cannot be crossed, right? We know that by the graph of the function. You cannot. So that's our vertical asymptote, x equals 1/2. That's the equation for it. And where is the horizontal asymptote? Horizontal asymptote is at, let me bring this down. Horizontal asymptote we found is at -1/3. Okay, so if -1 is here, -1/3 would be somewhere here. Somewhere here. 1/3 of the way from 0 to -1, almost. So right there. Okay, so I'm going to draw my horizontal asymptote with a dashed line, using a dashed line. I'm going to draw that. Like that. And the equation of this horizontal asymptote, let me put it here, y equals -1/3. Okay, so the equation of the vertical asymptote is that. The equation of the horizontal asymptote is that. And these are values that we have, right? 1/2 and -1/3. Okay. Now, the x-intercept was at -3, 0. That was our x-intercept. Remember, x-intercept was at -3, 0. So let's plot that point here. -3, 0 would be here. That's the x-intercept. right there, negative 3 comma 0. And how about the y-intercept? The y-intercept was at 0 comma 2. Right? 0 comma 2 would be this here. 0 comma 2. Right? Okay, so let's draw a graph of this rational function. So one piece, we can clearly see where it's going, right? One piece, it's going to come from here, go through that point, then go through this point and go this way. So like that. So of course with a computer, when we do this, it's going to be much smoother than what I've done here. But that's one piece. As we were talking about this earlier, every rational function has a split graph. So if one is on that side, then the other piece has to be on this side, right? So let's draw it. So the other piece is going to be over here, like that. So this piece turned out to be a more smooth line here. That one was not so smooth. But so those intercepts tell us where one piece is. But because we know with rational functions, the graph is always a split, and the other piece is always on the opposite side, so the other piece has to be here. Okay. Okay, so let's graph this function 2x plus 6 over minus 6 plus 3 on the computer for a better graph. And we're going to plot the asymptotes as well as the intercepts too. It'll help us get a better feel for this type of function and their graphs. Okay, so we had r of x equals 2x plus 6 divided by minus 6x plus 3. Right, like that. So look how nice and smooth these lines are as opposed to what I did, but that's that. So now let's put in the asymptotes that we found, right? The vertical asymptote was x equals 1 over 2, right there. You can see clearly that the lines are approaching it, these lines of the rational function. The horizontal asymptote was equal to y equals to minus 1/3, right there. You can see it clearly that the lines of the graph approach it like that. Okay. So this first piece, look how nice and smooth it is on the computer, and how nicely it approaches the vertical asymptote on this side, the blue line, and how nicely it approaches the green line, which is the horizontal asymptote. Okay, like that. So let's also snap to the x and y intercepts that we found. We found that the x-intercept is at negative 3 comma 0. Right there, we can see the transition, right? And the y-intercept, we found that was 0 comma 2. You can already see it up here, but let's snap to it. So 0 comma 2, right there. And let's label it. Okay, like that. Maybe we can zoom in a little more. Yep, right there. So you can see the x and y intercepts, the blue line, which is the vertical asymptote, the green line, which is the horizontal asymptote, and of course the graph itself, which is shown in red. Okay. I'm sure you agree that this graph looks a lot better than what I did on paper. Okay, so let's go back to the dot camera for the next example. Okay, so here we want to do the same thing. We're going to factor the numerator if it's applicable, factor the denominator if it's applicable, find the x and y intercepts, find the asymptotes, and then graph this function. Okay, so clearly we can factor the numerator, right? Let's do that. So this will be x times x plus 2 divided by x minus 1. Now let's find the x-intercept. I'm going to save some space this time by starting from above here, if you don't mind. So let me start here, x-intercept. That way I'll have more room for the graph. X-intercept is when y equals 0. So that means r of x equals 0. So 0 equals all of that, x times x plus 2 divided by x minus 1. So when is a fraction equal to 0? When the numerator is equal to 0. So this equation tells us that that numerator must be equal to 0. So from this, we can set each factor equal to 0 and solve for it, right? If you set x equals to 0, you end up with x equals 0 as one solution. And if you set x plus 2 equals 0, then you end up with x equals minus 2, right? So our x-intercepts are 0, 0, y 0, x equals 0, that's that. And also minus 2, 0. So these are the two x-intercepts here. Okay, 0, 0 and minus 2, 0. So now let's find the y-intercept. The y-intercept happens when x equals 0, right? So let's substitute for x everywhere here. I'm sure you can see where it's going. It's going to end up being 0. So y equals 0 squared plus 2 times 0 divided by 0 minus 1. So this is 0 over minus 1, which is 0. 0 divided by anything is 0. So the y-intercept is 0, 0. This is the value of y. And x we substituted for with 0. So 0, 0, which is that one. So 0, 0 is both the x-intercept and the y-intercept. Like that. Okay. So let's find the asymptotes. The easiest asymptote to find is the vertical asymptote. So let's find that first. That happens, vertical asymptote happens when the denominator is equal to 0. Is equal to 0. Okay? So let's find that out. Let's find when that happens. So x minus 1 is the denominator, right? X minus 1 equals to 0. That means x equals 1. So that is the vertical asymptote right there. X equals 1, we have a vertical asymptote. So then for horizontal asymptote, we have to see whether we have one or not. So looking at this original function, the leading term is x squared in the numerator, and the leading term in the denominator is x, right? So the degree of the leading term in the numerator is higher than the degree of the leading term in the denominator. What happens when this occurs? When the degree of the numerator is larger than the degree of the denominator? Let's go back to our description. Right? Remember that? So let's look at these three cases. If the degree or the highest power of p of x is larger, p of x is the numerator, that's all. P of x is the numerator, q of x is the denominator. So if the degree of p of x is larger than the degree of q of x, which is the case we have now, then there is no horizontal asymptote, and instead there is a slant asymptote. Okay, so in this case, we don't have a horizontal asymptote. Instead, we have a slant asymptote. So, and then how do we find the slant asymptote? Given this, use either the long division or synthetic division to find the slant asymptote. Let's do that. Okay, so we're going to, so this would be the horizontal asymptote. So let me quickly try to summarize what we just discussed, which is the degree of the numerator is higher than the degree of the denominator. Therefore, there is no horizontal asymptote. Instead, we have a slant asymptote. Okay, so let's find that. So for that, we're going to use the long division. We can use, in this case, we can use synthetic division too. So the slant asymptote, so x squared plus 2x divided by x minus 1, right? So if I cover that, the other term, what should I put up here to multiply by x to get x squared? Well, just x, right? Just multiplying x by that will give us that. But we need to distribute the x into minus 1 as well. So we have x squared, x times x squared, x times minus 1 minus x. Put parentheses around that and put a minus in front. Then x squared minus x squared. What do we get? We get 0, right? Those two add up to 0. Then 2x minus minus x. This minus will make this minus x positive x. So 2x plus x is 3x. Okay, that's all we have. So what should we put up here to multiply by this x to get 3x? Well, there's only one possibility, so plus 3. So 3 times x would be 3x. 3 times minus 1 minus 3, right? So put a parenthesis around this and a subtraction here. And let's subtract. We have 3x minus 3x, they add up to 0. Right? Is there a constant up here? No. So the only constant we have left is minus 3, which is positive 3. And this is going to be our remainder. So that is remainder. Okay? So the quotient is the slant asymptote. So let me box this. So x plus 3, or the quotient, y equals x plus 3 is the slant asymptote. There. Okay? That's our slant asymptote. So now we have everything we need to plot this rational function. We have the intercepts, we have the vertical asymptote, the slant asymptote. So let's graph it. I hope I can plot everything here in this space that I have left. Let's see. But I should be able to do it because these are nice, easy numbers, right? X equals 1, 0, 0, minus 2, comma 0. These are really easy numbers. So I should be able to fit everything here. X. Okay, so now let me increment. I'm just going to do 2 increments, 1 and 2, 1 and 2. Okay, so maybe 1, 2, 3. 1, 2, 3. 1, 2, 3. And so 1, 2, 3. And then, of course, 1, 2, 3. My increments are not perfect, so then I'm off here. So 1, 2, 3. These all should be the same length, but they're not. I know they're not. Okay, so given these increments, let's first plot our asymptotes. The vertical asymptote first. So vertical asymptote was x equals 1, right there. So that would be a line that goes right through x equals 1. And I'm going to draw it as a dashed line. Like that. And this is x equals 1. Right? The slant asymptote, that one. So let's find where the x and y intercepts are for this straight line. Right? So we can quickly do that. So if x equals 0, then y equals 3. So 0, comma 3 is the y-intercept for the slant asymptote. So that would be here. So the slant asymptote is going to intersect the y-axis here at 0, comma 3. This is an easy equation, right? So we can easily find the x and y intercepts. So if y equals 0, then x equals negative 3. So negative 3, comma 0, comma 0 is the x-intercept. So that would be here, right? Negative 3, comma 0 would be the x-intercept of the slant asymptote. 0, comma 3 would be the y intercept of the slant asymptote, because we need to know where that line is, right? Okay, so I'm going to draw a slant dashed line through those 2 points. And then let me also extend, because now that I know where the asymptotes are, I need to extend my vertical asymptote a little more, like that. Okay, so these are our vertical and slant asymptotes. Now let's find where the x and y intercepts are. So the x-intercepts were at 0, 0 and negative 2, 0, right? Let's plot those. 0, 0 is very easy. It's right there. That's 0, 0. And also negative 2, 0 would be right there. Okay? So those are the x-intercepts. How about the y-intercept? The y-intercept we found is 0, 0, which is equal to this one of the x-intercepts. So it would be right there. Okay, right there. Okay, so we can now draw the first piece, and the other piece would be on the other side, right? So let me draw this piece first. So it looks like this is how this is going to go. It's going to go like that. Then it's going to, this line is going to come and do this, go through that intercept, and then come back and do that. Okay, let me move this up a little bit. So that's as best as I can draw it, like that. So that's one of the pieces. We know with rational functions, we always have more than one piece to the graph. So where is the other piece? Well, the other piece has to be, let me try to put this on the screen, has to be here, right? It can't be anywhere else. That's where the line is going to be asymptotic, the graph is going to be asymptotic towards the vertical and then the slant asymptote. So the other line has to be here, right there. Okay? So that's the graph of that rational function. Okay, maybe I can move it up a little bit like that. Okay, so let's now graph the same function in the computer, and let's look at a much better graph. Okay, so we have, this was the function, rational function r of x equals x squared plus 2x divided by x minus 1. Okay, and if you can see just one piece of this because I'm zoomed in too much. Let me zoom out. Right there. There is the second piece. Do you see that? So that's both pieces of this. That's both pieces of this. But let's plot our asymptotes first, and then we'll plot the intercepts as well. So the vertical asymptote is easier. X equals 1 right there, right? You can see that. Then let's plot the slant asymptote, which was, what was it? It was y equals x plus 3, right there, right? You can see things come together, right? Let me bring it to the center. You can see the blue line, which is the vertical asymptote, and the green line, which is the slant asymptote. Of course, there should not be, or there must not be, a horizontal asymptote, and we don't see that, right? So let's also plot the x and y intercepts. So actually x-intercepts will take care of the y-intercept as well. So we have -2, 0, right? That's the x-intercept right there, the purple dot. And of course, the origin is the other intercept right there. Okay. Okay. So that's how it looks. Okay, we have come to the conclusion of another section, and I thank you for persisting through this section 3.7. For now, have a nice day. But when we will come back, we will look at section 4.1. Please keep in mind to read the section from your book before watching the video or coming to class or attending class. Thank you for that, and have a nice day, and I'll see you next time.